Hello everyone, welcome back to a new video. In this video we will be solving some of the questions from chapter 5. So we have question 1. It says if you have a circle-like shape, flat mirror, can you see the image of things around you without necessarily seeing your image? Yes, you can, just by positioning your eyes above the or to the edge of the mirror. Okay, and let's say this is your eyes. These are your eyes. And you have light reflection, okay, from the mirror. Okay, it's the light reflection. You can see that the image is going to be formed like this. We have question 21. Question 21, it says, when you shine a flashlight across a room, you see the beam of light on the wall. Why do you not see the light in the air? Because gas is transparent, or the air is transparent, and sometimes, in rare cases, when there is too much dust in the air, you can see slightly the reflection of light, okay? But normally, there is no reflection of light because the air is transparent. While we can see the reflection of light on other objects, such as a wall, a table, or any other object. How can an object be specular reflector if for electromagnetic waves, yet be diffuse for others? So how can the question says, how can an object be specular for some electromagnetic waves but diffuse for others? Well, this depends on the roughness of the object. If the irregularities in the roughness of the object are small, then the object is going to be specular. If the irregularities are going to be more, okay, if they increase, then it's going to be diffuse, okay? So if you have more roughness, the object is going to be diffuse, okay? But we have to also consider the wavelength of the electromagnetic wave that we have. A flat mirror that is 0.85 meter tall is attached to a wall so that its upper edge is 1.7 meter. So you have a mirror, okay, let me erase that. You have a mirror which is 1.7 meters tall, okay? It's 0.85 meters tall, but it's attached to a wall which is 1.7 meters, okay? So let's say this is the mirror. The height of it is equal to 0.85 meters. The height of it from the wall is equal to 1.7 meters, okay? Use the reflection of the law of reflection and ray diagram to determine if the mirror will show a person who is 1.7 meters tall, his or her complete reflection. So we have 1.7 meter, okay, and this is the height of the mirror, and we have 0.85 meter, which is the height of the mirror, okay? 1.7 is how high the mirror is attached to the wall, okay? So a person basically can simply see themselves if they're 1.7 meters tall, okay? We have to consider also the distance from the mirror, okay? And for the person to see the reflection, a light ray from the top of from the upside of the mirror should reflect their eyes. And in order for them to see their feet, okay, a ray from the bottom of the mirror should reflect the eyes, okay? That is how they can see themselves. You should also consider the distance, okay? As you can see, the more you get closer to a mirror, the bigger your image becomes, okay? So you cannot see other parts of your body. So you should also consider the distance. We have question 25. Two flat mirrors make an angle of 90 with each other, as diagrammed at right. An incoming ray makes an angle of 35 with the normal of mirror A. Use a reflection of light to determine the angle of reflection from mirror B. What is unusual about the incoming and reflected rays of light for this arrangement of mirrors? So we have two mirrors. This is the first mirror. And we have what? We have the angle of incoming ray, which is equal to 35. Of course, this is going to be the normal line that we have here. This is the angle, which is equal to 35. It says, what is the angle of the reflection for this mirror? So the angle of reflection is going to be the same. As you see, this is going to be 35 also here. And of course, we have a second mirror, mirror B. This ray is going to be reflected like this, okay? But first do this. We put this as the incoming ray. This is going to be reflected ray. But for mirror B, this is going to be incoming ray. Okay, it's coming from this mirror. So this is going to be what? This is going to be having a normal line like this. This is the normal line. Okay, this is the incoming ray. So this is going to be how much? How do we know how much is this? We have how many? It says it's the angle between the two mirrors is equal to 90. Okay, so 90 minus 35, we have 55. So the angle is going to be how much? It's going to be 55. Okay, what is unusual about this case is that the incoming ray from mirror A and the reflected ray from mirror B are parallel. Okay, that is what's unusual. We have two mirrors, that's why. If you walk 1.2 meters per second toward the flat mirror, how fast does your image above with the respective mirror move? In what direction does your image move with respect to you? So we talked about this, and we said that if you have, for example, let's say you are going 1.2 meters. This is with respect, careful, this is with respect to the mirror, okay? The image with respect to you, okay, sorry. So you have this. If you go 1.2 meters per second, of course the image is also going to be moving 1.2 meters per second. So if you move, okay, what is going to be the speed of the image? It's going to be how much? It's going to be twice the speed of the observer. So it's going to be 1.2 plus 1.2. It's going to be 2.4 meters per second. Okay, and it's going to this direction. We have question 27. It says, why do the images produced by two opposing flat mirrors appear to be progressively smaller? Because of the reflection, or the multiple reflection of light rays from each, for many times. Okay, for example, you have one ray. Okay, let's say you have two mirrors like this. Okay, the ray is coming and it's going to be reflected, but this process is going to happen more than once, and that is why the image is going to be getting smaller and smaller. A boy approaches a flat mirror with a speed of 1 meter per second. It's the same question as 26. At what speed does the image of the boy approach the mirror? Okay, so it's going to be 1. So it's going to be 2 meters per second. Okay, twice the speed of the boy. What is the speed of the image relative to the boy? Okay, what's the speed of the image relative to the boy? Sorry, just a mistake here. It says here, what is the speed of the image of the boy that approaches the mirror? So here we have mirror, not the boy. It's not compared to the boy. It's compared to the mirror. It's not compared to the image. It's compared to the boy. So it's going to be what? The boy is also going to move 1 meter per second. What is the speed of the image relative to the boy? Okay, this time we have the image and we have the boy. So it's going to be twice the speed of it. If the boy stops moving and the mirror is moving towards the boy at the speed of 1 meter per second, what is the speed of the image with respect to the mirror? So it's going to be still 2 meters per second. Okay, which type of mirror should be used to project moving images on a large screen? Concave mirrors. The only type of mirror that can project, its image be projected onto a physical screen is a concave mirror. Okay, because it has real images. If an object is placed outside the focal length of a concave mirror, which type of image will be formed? Will it be in front of or behind the mirror? It's going to be, of course, in front of the mirror, and because it's outside the focal length, it is going to be inverted and real. Okay. We have question 31. Can you use a convex mirror to burn a hole in a paper by using light rays from the sun at the mirror's focal point? No, you cannot, because convex mirror only diverges light rays. It cannot converge light rays. A convex mirror, for question 31, you can do that with a concave mirror, okay? Because a concave mirror is able to converge all light rays at one point. A convex mirror forms an image from a real object. Can the image ever be larger than the object? No, because light rays are spreading out and it is impossible for the image to be larger than the object. Why are parabolic mirrors preferred over spherical concave mirrors for use in reflecting telescopes? Because parabolic mirrors are better at converging light rays than concave mirrors. That is why they are used. I think this is it. If you have any questions, okay, regarding, because we have many questions to cover, okay, and it's going to be a long video. I'm not going to solve all the questions, but if you have any questions regarding chapter 5 review and assess, make sure to comment below, okay? I will be happy to answer all of your questions, okay, because I'm going to be moving on to chapter 6, and I don't think it's necessary to solve all the questions. And you just have to, if you have understood how to deal with finding the image distance, the object distance, position, and the focal length, I think that's enough, okay? Most of the questions are repeated, and they're really easy. So in the next video, I'm going to be moving on to chapter 6, and we'll be hopefully completing all the chapters. See you in the next video.